Hello, welcome again. We are solving some questions of fluid mechanics and machinery. The topic is fluid statics, properties, manometry and buoyancy. Question number 5 is an incompressible fluid kinematic viscosity 7.4 × 10⁻⁷ meter square per second, specific gravity 0.88 is held between two parallel plates. If the top plate is moved with a velocity of 0.5 meter per second, while the bottom one is held stationary, the fluid attains a linear velocity profile in the gap of 0.5 mm between these plates. The shear stress in Pascal on the surface of the top plate is option A is 0.651 10 to the minus 3, option B 0.651, option C 6.51, option D 6.651 10 to the 3. So this is the Newtonian fluid relation, that is tau is equal to mu dU by dy. As viscosity, mu here viscosity, and here the kinematic viscosity is given, that is 7.4 × 10⁻⁷, and specific gravity is given 0.88. So uh, so the the density is rho specific gravity into viscosity, specific gravity into density of fluid, that is 880 kilogram per meter cube. So mu is your rho into that kinematic viscosity. So the dynamic viscosity is 880 into 7.4 10 to the minus 7. Okay, and now the change in velocity is, or we can say that the velocity at a distance 0.5 mm is 0.5 meter per second, and the gap is 0.5 mm, or it is in meter is 0.005 meter. Okay, so tau is equal to 880 into 7.4 into the minus 7 into 0.5 divided by 0.0005, so that is 0.651 Pascal. Okay, so answer is option B. Okay. Next, a laminar flow takes place between closely spaced parallel plates as shown in figure below. The velocity profile is given by u is equal to v y by h. The gap height h is 5 mm, and the space is filled with oil. Specific gravity 0.86, viscosity mu is equal to 2 × 10⁻⁴ Newton second per meter square. The bottom plate is stationary. Top plate moves with a steady velocity of 5 centimeter per second. The area of plate is 0.25 meter square. The power required to keep the plate in steady motion is option A 5 × 10⁻⁴ watt, option B 10⁻⁵ 10⁻⁵ watt, option C 2.5 into 10⁻⁵ watt, option D 5 into 10⁻⁵ watt. So here the viscosity is 2 into 10⁻⁴ Newton second per meter square, and the gap is given as 5 mm. Okay, so it is 5 by 1000 meters. Okay, and the velocity of the top layer, or we can say the velocity with respect to stationary plate, is 5 centimeter per second, or 5 by 100 meter per second. So according to Newton law, again taking the same formula, that is tau is equal to mu du by dy, putting the value of mu du and dy, the shear stress is 2 × 10⁻³ Newton per meter square, and area of plate is given as 0.25. So this is your plate. Okay, and the area is given parallel to the floor, and the shear stress we have find out. Okay, so the area of plate is parallel to flow, parallel to shear stress, or the force of plate is this. Okay, so 2 × 10⁻³ into 0.25, that is 0.5 × 10⁻³, that is force of plate, and the power dot is force into velocity. So 0.5 × 10⁻³ into 5 by 1000, so 5 by 100, that is 2.5 × 10⁻⁵ watt. So power dot is C. So answer is C. Next, the pressure gauges G1 and G2 installed on the system shows pressure of Pg1 5 bar and Pg2 1 bar. The value of unknown pressure P is atmospheric pressure 1.01 bar, and this is your P, this is G1, this is G2. These are the pressure gauges. Okay, two pressure gauges. Option A 1.01 bar, option B 2.01 bar, option C 5 bar, and option D 7.01 bar. So this is your G2. Okay, and the atmospheric pressure is 1.01 bar. Okay, and it is given that Pg1 is 5 bar and Pg2 is 1 bar. Pg1 is 5 bar and it is 1 bar. Okay, so this is your 1 bar and this is your 5 bar, and for this atmospheric pressure is 1.01 bar. Okay, so and for this atmospheric pressure is 5 bar. Okay, so total pressure at this will measure the gauge pressure of this, gauge pressure of this is 5 bar, and the atmospheric pressure here is and this is measuring 1 bar, and so it is measuring its gauge pressure. So total pressure here is 1 bar plus 1.01 bar. Okay, so that is 2.01 bar. So this will behave as an atmospheric pressure for this gauge. Okay, so the total pressure inside the inside this tank is gauge pressure plus its atmospheric pressure, that is 1.01 plus 1, that is 2.01, so that is 7.01 bar. So the total pressure at P is your 7.01 bar. So answer is option D. Next, a U-tube manometer with a small quantity of mercury is used to the static pressure difference between two locations A and B in a conical section through which an incompressible flow flows. At a particular flow rate, the mercury column appears as shown in the figure. The density of mercury is 13600 kilogram per meter cube and G is 9.81 meter per second cube. Which of the following is correct? So this is A, this is B. Option A, flow direction is A to B and PA minus PB is 20 kPa. Option B, flow direction is B to A and PA minus PB is 1.4 kPa. Option C, the flow direction is A to B and PB minus PA is 20 kPa. Option D, the flow direction is B to A and PB minus PA is 1.4 kPa. So here by applying the by equating the head at 1 1, we can find out the pressure difference PA and PB. So from the left limb, the total head is total pressure is PA plus this head is the pressure due to this head, that is 150 by 1000 into rho g. Okay, and this is your PB. PB is your rho m means mercury. Okay, into 150,000 again same thing. Okay, so above them is same fluid, so that's why we have not taken this quantity in this quantity. So we have taken only the PA and PB and this difference in head. Okay, here there is mercury and here there is water for 1%. Okay, so now this is your PA, this is your PB, and PA minus PB is your if you put the value of rho m as 13.6 into 1000 and rho as 1000. Okay, so we get this as